Uh, Thanks for the organizers to organizing these emerging topics, and also thanks for the previous speakers to set up everything for me. So it make my life so much easier. Okay. So I'm going to try to present the proof of the control of eigenfunctions on hyperbolic surfaces. The theorem is already discussed yesterday in Simon's talk, and the basic strategy is also discussed. But I'm trying to give as much detail as I can in this talk. Okay. So maybe let me first state the kind of the easy version of the theorem. So, okay, so. Okay, so let me start with the setup of the basic setup. So in my talk, M is always a compact hyperbolic surface. And connected without boundary. And we'll consider the eigenfunctions on them. Eventually we will not be discussing eigenfunctions at all, but for now, to say the theorems, I want to discuss the eigenfunctions. The minus Laplacian will be the Laplacian operator, obviously. And we'll consider the eigenfunctions on this manifold for the Laplacian in the semi-classical limit when lambda go to infinity. And as we discussed yesterday, we want to do a semi-classical reduction by simply, lambda square, using lambda as frequency, by multiply this equation by h square, so it becomes minus h square minus Laplacian minus 1 u equals 0. So in this setting, h will be lambda inverse, which goes to 0. Okay, so so the control of eigenfunctions basically says the following. So that for any open, so U for any eigenfunction, it can be controlled uniformly in any open set. So for any open set U, which is not empty, we have the following. So there exists a constant which only depending on the manifold and the open set, such that if U is an eigenfunction, then it has at least a certain amount of mass in this open set, and uniformly for any eigenvalue. So, oh, sorry, yes, U. Sorry. And so this, we also have control for Schrodinger equations if you are interested in evolution equation. And actually I call this is the observability of Schrodinger equation. So again, M is a compact hyperbolic surface, and U is any open set which is not empty, the same setup. Then for any t greater than 0, there is a constant k which is only depending on m, omega, and t, such that for any initial data, its L2 norm can be bounded by the evolution and the Schrodinger flow, but only restricted on the on this open set U. Sorry, it's U again, and integrating from 0 to t, so integrating time. And from this, we have a so-called control result for Schrodinger equations. Okay. And so these both are kind of results on physical space, but our strategy is to go into the phase space and considering kind of a micro-local version of the control of eigenfunctions. Okay, so and this can also be formulated in terms of semi-classical measure. So another theorem which we can formulate is as follows. Sorry, which?
Square and the norm, I suppose.
Oh, square and the norm. Thank you. Okay. So if mu is any semi-classical measure for Laplacian eigenfunctions on compact hyperbolic surface M, then the support must be the the largest it can. So the whole unit sphere bundle. And in fact, we have a more quantitative statement, which basically says for any, again, open subset U in I star M, it's positive and it's actually greater or equal to a constant which only depends on U and M, but not on the semi-classical measure we are choosing. So potentially there could be many of them, but the hope, of course, is there is only one of them, which is the Liouville measure. But so far, it's we cannot do that. Okay. Okay.
Sorry, what exactly is the difference between the two statements?
Which statement?
One says that the measure of mu, the u is positive.
Right.
So what more does it say to put in a constant u and m? What else could it depend on?
Well, it could also, so if suppose there are like many
that are supported.
many different semi-classical measure, then
all
they will all have the same lower bound on each open set. So, okay. Okay, so so all of these results actually follows from one simple, or maybe not a simple, but a main estimate we have, a semi-classical version of this. You can say it's a semi-classical version of this control of eigenfunctions, but we set it for all functions, and we put it into the, if we want, the right-hand side of this equation, if u is not an eigenfunction. So. So the mean estimate is as follows. So for any functions on the phase space, and suppose it's not identically 0 on the unit sphere bundle, then there exists two constants, C and H0, both positive, and only depends on M and the function A we are choosing, such that for any h smaller than h0, we have the following control result. So any any function u in h2m, so its L2 norm can be controlled by the basically the mass of u on this micro-local cutoff. I have a constant here, C, and a constant time log 1 over h with minus h squared Laplacian minus 1 applies to u, the L2 norm. Okay. So so it's kind of automatically, if we choose eigenfunctions, this part will basically be 0. So we don't have this part. And if we choose A to be only dependent on x, then we get the control of eigenfunctions. And if we choose any A which kind of not vanishing on this U, will get this result. And for control of Schrodinger equation is more involved, but it's kind of a standard argument from work of Bielk and Zworsky in the black box setting, so it considered any setting. So this kind of result automatically gives you the control of Schrodinger equations. Okay. Okay, so that's so the goal of my talk is of course to try to prove this theorem using the fractal uncertainty principle. Okay, so does that make sense? Okay. Okay. So maybe let me first by review the strategy which already kind of presented by Samyang yesterday. So this is kind of so we think of this as some kind of control result of any sorry.
This statement would not be true for a finite area.
Which one? Sorry.
The first one.
This one?
Yes. Is it false for a finite area?
For finite, sorry.
Non-compact but finite area.
Right, I think it should be true, but it's
We
true.
have no idea.
Well, right, we have right,
So it changes.
right.
It's true.
It's probably true, but
Say we can prove it right now.
but we you know what I mean, we cannot really.
Once you go to finite area non-arithmetic, you don't know that the L2 norm is finite, so you have to start with.
No, but I mean this Schrodinger equation thing, that makes sense.
But the
Why
first
shouldn't it be
statement also makes sense for finite.
Right.
No, but this is a technical finite area.
Well, I guess if you have infinity, technically the semi-constant matter can propagate, go through the.
Propagator better than the wave propagator. I always like the wave operator. Be the same thing, or
If you put a wave operator, oh no, you cannot prove that. Basically, the control of wave equation is more or less equivalent to the thing I'm going to talk about called geometric control. So this is kind of without the condition without the geometric control. And the Schrodinger equation you can still do that, but the wave equation is not possible.
I mean, you've got to be very careful if you have a cusp, because if you have no discrete spectrum, actually you start with a disturbance in the wave equation, it will actually go out into the cusp. The whole energy will be kept, and then you don't have a lower bound. It's very dangerous.
Okay, so so maybe let me first state some notations that we have, and then I'll present what is kind of the general strategy we are going to use. So let me here. Okay, so so on this cotangent bundle, we will have a natural metric on this, and we'll always write this function p will be the kind of the norm of this this covector in this matrix, and capital P will be well essentially minus square root of minus h square Laplacian, which will be in our quantization I'll present a little bit later, which is the quantization of this P here. Of course, I'm kind of cheating here. Eventually, I'm only considering this thing near the co-sphere bundle, but doesn't really matter that much. Yes?
Another annoying question.
Okay.
What happens if you take another elliptic operator instead of minus? Coefficients, that's annoying.
Well,
So variable negative curvature is the big question.
Right.
Supposed to answer by the end of the week.
right. Right. So far we can only do like a constant curvature. So.
Can you add a potential?
Oh, if you can, if you want to add a potential, I think it's kind of actually quite easy. You can easily plug a potential in here if it's L infinity, because there's h squared here and you have h log omega h. So this is still small. Everything will still go through. Okay, so if you
Make a variable, if you
right, but if you put something larger than that,
keep the dynamics periodic, then they
Right. Right.
Right now they're using the constant curvature, if I understand quite seriously.
okay.
the question is, can you add a sub-principle?
Right. So if you add the potential is too small. Right.
If it's zero order term,
Okay, and And so for each of them, we'll have a dynamic. So the dynamic with the this symbol P is the Hamiltonian flow. And I'll normally call it a phi t. Let me see, so the up. Okay. HP. And this is nothing but a geodesic flow, if you want. So. Okay. And for this operator here, we'll have the unitary, basically it's kind of half wave group. So it's e to the minus it over h times capital P. Okay. Okay, so what's our strategy here? Let me leave this here. Okay, so we want to basically control any function on this manifold anywhere in this phase space. Right. And but there are only two things we can use. One is this where its a is. Another part is this other symbol, this p, if you want p squared minus 1 is. Okay. So basic thing is, I think yesterday Samuel already talked about the elliptic estimate. So basically, if you have if the part of B, if a part of U is on where A is on 0, it can be controlled by this part. And if the part of U where P squared minus 1 is on 0, it can be controlled by this part. Right? So this gives some basic part which are controlled. So. By the elliptic estimate, so we can control U on which A is on 0 and P squared minus 1 is on 0, which is exactly the if you want the complement of the cosphere bundle. Okay. So basically, our focus is on what happens on the cosphere bundle and A is 0. Okay. There's another thing which is basically kind of a propagation estimate. I'll explain in a moment, but I think Samuel already explained in some way yesterday. So basically, you can kind of propagate this A by this geodesic flow. And you can still control the kind of the flow out of this A is not 0 under this geodesic flow. So if you want, this is like the by now we need both of them, both the AU and
Okay, but this now becomes delicate, right? Because you want to know how much you could flow, etc.
Exactly. So I will explain this in detail, but this I'm trying to present the strategy here. So this is part, and of course let's just for a moment pretend that we can propagate everywhere for any time, but that doesn't mean we'll control everything. There could still be things left, and that's the the main obstacle here. So here is A is not 0. If we have a closed orbit which missing this A is not 0, then by propagation estimate, no matter how long we want to propagate, we cannot never control this part. Okay, but the point is, if we propagate this long enough, like eventually we want to basically in log 1 over h times rho. Rho is a small rho is a number which close to 1. Then the last part is where FUP comes to kind of rescue us. The part which is left, we'll use FUP to deal with the remaining part. Okay, so this will be our strategy. And basically, what we are claiming is what is left will be a kind of a very fractal set in many, in like at least you can think of in at least in 2 different directions, which are fractal. Okay. So maybe let me first briefly review what is this quantization, and especially what happened this morning about this quantization of these rough symbols and stuff. Okay. So. Okay. So I think this morning, Simon already talked about the case on the real line. Basically, if we have a smooth symbol which may depend on h, but in a very mild way, then we can always associate to a family of operators depending on h, which are acting on L2. Okay, there's a exact formula for that, and of course here we are on a manifold, but a compact manifold. So there is also a way to define such a thing on a compact manifold. So roughly speaking, is you do this by you use a kind of partition of unity to cut it into coordinates and then piece them together. So on M, so for any symbol which is a smooth function on the cotangent bundle, we can associate to an operator which acting on L2 of M. Okay, and the point is, as long as if you are in a very nice symbol class, all the properties of the ones on Euclidean space kind of more or less carry out into the manifold, compact manifold case. Okay, but for us, like, nice symbols are not enough. We also need these rough symbols. So, okay. So there is a symbol Simon introduced this morning, which is called SL0 rho, which is a symbol which, if we differentiate in one of x and c, then it will start to lose powers of h. So I think L0 is the symbol which we lose the power of h to the minus rho every time we differentiate in x. So, okay. And rho is always between, not in cosine, right? So, okay, so we kind of pretend everything is compact supported, so everything will be nice. So in this case, we don't care about that. Yes. Well.
C is homogeneous.
Right. So well, you could also think in case of C is homogeneous if you want, but for us, we want to kind of if we want just kind of the symptotic parameter, we are already replaced using h. So somehow, if you want C over h is really the previous.
Probably like me.
Okay.
Studied the subject not with the h, but the way it was first introduced.
Right. So it's
the theory of pseudo.
Sure, that was its second.
And every time I try to read these things, I'm driven nuts.
Well, it was first started by quantum mechanicians, who did have an H. So
Right.
Yes.
The paper of
Which
Lax.
came first?
The most important paper was 57 of Lax, and then Hollander 62. 60.
Actually, here in my
Right.
biology, that's the definition.
No, you're right. Pseudo-differential operators.
Right. But in any case,
Nuremberg did the homogeneous.
so if you want, the support of A could be like lying in all this fractal set, which kind of collection of intervals in x direction of, I guess this will be h to the minus rho. And this direction will be very smooth, and this will be a rough direction.
Can I ask you a question?
Yes?
Is this going to arise because you dilate the symbol A,
No, this will rise because eventually will propagate A in the geodesic. Okay, so it will come in a moment. So okay, and also there is another one which is L1 row, which basically switches this to K. So okay, so the L1 row of course will be the one which has support in this direction. And the key point of this morning's talk is that they do not talk to each other directly like a normal like a symbol calculus. So they cannot be related to the two symbol class cannot be related directly. Okay.
Why is that L0 and L1? Is there any?
This is the notation Samuel is using, but I'm not sure. Okay, what's the?
Lagrangian plane. It's a
Right. So eventually there will be Lagrangian. So it's L0 L1.
Right. Wait 15 seconds and then.
Okay.
Look here.
Okay, so on M we'll introduce similar things. So basically, in this case, we'll fix a certain Lagrangian. So actually, Lagrangian foliation. Which means at each point, it is a Lagrangian subspace of the tangent space of the phase space, and it can be integrated to the Lagrangian leaves. So instead of this kind of picture, which vertical Lagrangian and the horizontal Lagrangian leaves will have such like a curved Lagrangian leaves. Okay, and okay, so let me keep it here. So for this, we can also define similar kind of rough symbols, which are let me see, which are smooth in this Lagrangian direction, but rough in this transversal direction. So basically, it means if we differentiate this in differentiate A with all the V's or W's are vector fields, but W are tangent to L, then we only lose powers of H when we differentiate in B but not in W. So this would be less or equal to CJKH to the minus rho J. So only lose powers when we differentiate in B direction but not in W direction. And because of like it's a foliation, you can integrate it, so you can doesn't matter which order you are choosing. So okay. Okay, so so what will be the fractal uncertainty principle? So this morning we see in this situation, which basically says,
But
okay.
shouldn't you have like two transverse Lagrangian foliations?
Yes. Eventually, when we formulate FUP, there will be two of them. But here is kind of for any Lagrangian, we can define such a thing.
So just no change if you use the W's.
I mean,
Defining
so this is kind of a general definition for any Lagrangian.
What can we
What-
quantize?
What can be quantized, right? So,
a class of symbol which is somehow
right. So if we choose L to be L0, that will be that one. L choose to be L1 will be the other one. So, okay. And to formulate FUP, of course, we need two different Lagrangians. So in this morning, we have the case when we have the vertical one, and horizontal one. And although they do not talk to each other, but if we multiply them together, we'll get this FUP thing. Okay, so it's basically of H of AX of H of AY L2, that's all equal to H beta to the, because we have this row here, a moment, but you'll lose something here. So X, Y, a new porous set in 0 and 1, and from scales H to the row to 1, and AX is kind of in the support of AX is in, well, the set C belongs to X, and AX is in this L1 row, and same for AY, is in X, Y, AY is in S. Okay, so this is the fractal uncertainty principle proved this morning. So in this one-dimensional situation, and now we can adapt this into our situation. So if we have two transversal Lagrangian foliation, and then we can basically putting this into our into this manifold, into these two quantization we have. So okay, so I probably don't have enough space here, but let me try this. And Lx, so x and y will be like here, so x, y, like still like this, and Lx, Ly will be two Lagrangian foliation. The support of Ax, you can think of Psi as a function and Psi are two functions. Locally, which kind of project into this direction. The support is in X and support is in Y in this in one-dimensional polar set, and of course we want Ax to be in this Ax and Y in the corresponding symbol class. And the key condition is this X and Lx and Ly cannot be the same thing; they have to be transversal to each other. One way to formulate that is Psi not only transversal but their Poisson bracket has to be not 0. So we can, by a symplectic change of coordinate, basically we can put one of them to be X, another one to be Psi. So it will go back to this situation.
I'm not understanding because I'm lacking something. What is psi of x?
Psi X and Psi Y are two functions, which basically kind of project into one direction. It should be, the support should be lies on this Proust set, one-dimensional Proust set. So it's kind of a Proust in this one direction.
You can make it draw it on the picture.
Oh, right, exactly.
There is actually an unfinished picture.
Right, there is one finished picture here. So this will be the Psi X direction. So this would be this. This will be Psi X direction, and this will be Psi Y direction. And I guess Ax will be kind of near H row neighborhood of on these leaves, and Ay, the support of Ay will be on these leaves.
So the space is three-dimensional.
Yes, actually it's 4-dimensional, but we only have two directions. They are kind of porous. In the other direction,
What is the
No, you're saying 4 is the cotangent.
4 is the cotangent direction of the cotangent bundle. There are four. It's 4-dimensional.
The energy is fixed.
If energy fixed is 3-dimensional, but there is also another direction which does not come into this picture here. That's basically kind of the flow direction. And that direction, well, when we do this, we basically kind of integrating in using this for each of this.
Well, one is the flow, one is stable, and one is
Yes, I'm going to explain that in a moment which direction I'm going to use.
Psi x and psi y generating functions?
Well, they are kind of just tell you the direction of
How are they related to Lx and Ly?
Well,
Psi x should be constant on these.
right, Psi X and should be constant on Lx, Psi Y should be constant on Ly.
There are some conditions not written there which
Right.
are satisfied in our case, but which are written but don't know.
Okay, so let me find which page here. Okay, so so let me maybe first explain a little bit about this propagation estimate, the Egorov theorem, and then we do it.
So the X and Y are the porous sets, and
Right.
you're looking at psi inverse of them, so you're sort of transferring the
Right.
0, 1 onto
Right.
the leaves.
Right, so we are just basically saying that the transversal section, any transversal section is kind of porous, if you want. So okay, so Okay, so let me try to explain this Egorov theorem and the propagation and how this works, and we'll see when we do it for a long time, this will kind of naturally coming up. Okay, so okay. Okay, so I'm not going to present the whole Egorov theorem, but only a very simple version. So suppose I have a symbol, let's say compact supported and smooth function, and then we want to kind of conjugate this operator of by quantization of A by the flow, by this the half wave group. And what we will get is actually something very nice. It's basically we propagate A by the geodesic flow, modulo a lower order term. So H. So let's say L2 to L2. Okay. So actually the proof of this is very simple. So I can show you in kind of in one line or maybe two lines. So. Okay, so we want to prove this result. We can move u minus t and ut to this side, and basically put everything has t together, and because they are unitary things. So we just need to prove the following: u minus t, ut. Okay, of course, t equals 0. The two sides are the same. There's no error there. And want to prove for some t, let's say t is a fixed number, like bounded in H, okay, for our case now. Then we just need to differentiate in t and say the derivative is O of H. Okay, so what is the derivative of this in t? I think, let me see, this is not t, I think. Yes, okay. There are three things to differentiate. If we differentiate this one, we'll pick up a p there. So we're going to get minus a h p. And if we differentiate in this one, we basically get replace this by the derivative of this, which is a Hamiltonian vector field applied to A. So this part will still have op H of A. And finally, if we differentiate this one, of course, we get another p, but with a negative sign. So plus I h, and I switch the order of the thing. U minus t. Okay. We have three terms, and this one basically gives the commutator of the two. And by the quantization, commutator corresponding to exactly this is a Poisson bracket, so of the two. So they are basically agrees in the main order. So this is O of H. Okay. So that's kind of a simple version of Egorov theorem. Okay. So let me. Okay. So how does this propagation, this part propagation works? Okay, so let me introduce a notation. I think we borrowed from the. We also borrowed from an assignment paper. So if we have a bounded operator A, then we write A bracket T to be U minus T by conjugate A by this half wave group in time T. Okay, so this actually can be written much simpler. But how do we control? So the question is basically how do we control AT using A and kind of the generator of the half group? It's still a kind of I guess it's a very similar calculation of this by taking derivative. but it's kind of worth to write down what's the statement here. If I can find it actually here. Okay, let me write the proposition. Okay, so it's a so basically the part of AT can be controlled by A, and the part of which and this minus h squared plus minus I applies to U, but times the time you propagate t divided by h is a constant. Okay, so again this is basically the same proof or similar proof like this. You write this and differentiate, and you'll see what's going on. So it's like you're trying to control a function on R, fx, and you want to control it by f0 plus f prime x between 0 to x. It's essentially the same thing. Okay. Okay. Now, basically, from these two arguments, these two simple statements here, we can essentially get something similar to this under a stronger condition. And actually, we can get something better without this log 1 over h. The condition, of course, is if there is a time we propagate to time t, we cover everything, then we'll have this statement without this log 1 over h. So that's called the geometric control condition. And I don't think I have enough time to write it down, but I think I'll pass this. So, so the game, of course, is we are trying to, in the situation where there is no geometric control condition, we still want to prove a slightly weaker result here. Okay, and the game is now we don't propagate to a fixed time t, but we propagate to time rho times log 1 over h, and that will give in this equation, this estimate here will give us this part, and we see what do we cover, and then we see what's remaining. Okay. Okay. And of course, the remaining part we are hoping to get this. But first of all, let me mention what happens if we propagate a nice symbol up to time log 1 over h. Okay. So what's happening? Let me see. So maybe I should mention a little bit of the dynamics of the geodesic flow here. Okay. I really shouldn't print it in two sides. So okay. Okay. Right. Oh, here. Okay. So so basically, on T star m, we kind of fix a very specific coordinate. It's given by 4 vectors. So we have the flow direction, the HP direction, and there will also be the 2 stable and unstable direction, U plus and U minus. And there is a final direction D, which is kind of going dilation in the fiber direction. So it's like a C D. Partial right. So, okay. And they have a very simple commutator relation. So U plus minus D. So all the three other things will commute with D. But the key, of course, is if we commute plus, right. If we commute HP with U plus minus, we get plus minus U plus minus. And if we translate this in the flow into this flow generated by HP U plus U minus, we'll get okay. We'll see why this U plus minus are stable and unstable direction. So if we propagate u plus in the flow forward by t, then it will become e to the minus t u plus, so it becomes stable. And u minus becomes e to the plus t, so it's unstable. Okay. And of course, what happens will be this flow roughly it's a very hyperbolic thing. Actually, it has a fixed expansion rate and a contraction rate. So if you start with a domain where every direction you have size 1, then you propagate by time t, you get to something which in the stable direction, this will be like e to the t, and the unstable direction, it will be e to the minus t. Okay. And if this is kind of our support of A initially, then we propagate after time t equals rho to the times log 1 over h. This would becomes h to the rho, and this will becomes h to the minus rho. So it will become very smooth in this direction, but very rough in this direction. So that's exactly where our symbol class coming in, because in our symbol class we kind of basically require it in to be, we kind of allow it to be rough when you differentiate in one or in some direction. So the final result of this propagation will be, okay, so maybe let me write it here. So let's say if A is H independent, then if we propagate forwardly for time rho log of 1 over h uniformly from 0 to this, then A propagated by phi t will be in this Ls rho here, and Ls will be, we can choose this to be the span of, let me see, span is Ls HP with U plus. And similarly, we can do, if we propagate backwardly, we'll end up in the other one. So it will be LU of rho. Okay. And Egorov theorem can still be stated in this setting up to time rho log 1 over h. Of course, the quantization we have to use is in the quantization in these two classes. Okay. 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 So, of course, so what's left? Of course, I want to explain our approach. The more details about this FUP part, so where it is coming in. Actually, the argument is quite delicate. We kind of borrow some of the elements, many of the elements actually from Anna Thurman's argument here. So in their paper, in her paper, I think what he is trying to achieve an entropy lower bound. So he had to take a partition and a finite partition. But for us, we don't need to do that because we only want to control it in one part. And basically, we are seeing the rest is the other part. So we just had a partition, very simple partition of two parts. Okay, so let me see which part. I want to use maybe this one. Okay, so first we introduce this partition here. We have this T, maybe S star M. So let's forget everything away from S star M because this can always be controlled by elliptic estimate. And we'll partition it to the one where we have support of A. I mean A is not 0. And what's rest. And actually we pick one which can be controlled by A. So this would be our A1. Because we don't want to control everything by size. In semi-classical analysis, we want everything to be smooth, so we can do this simple calculus. So A1 and what rest A2 will be two operators. So and Aj is of Haj here, and A1 plus A2 will be identically 1, and they are both between 0 and 1. So each of the norm will be, well, constant. Okay. And the support of A1 is in A is not 0. So A1 represents the part which can be controlled by A, and A2 represents the rest. And another key part is we kind of want both A1 and A2. Well, neither of A1 and A2 can control everything. So we want to exist U1 and U2 in this open set such that Uj intersect it's not intersecting with the spot of Aj. So each of A1 and A2 will kind of miss a hold here. And now we do this dynamical refinement argument of Anna Thurman. So we basically put the set of the, okay, yes. For any positive integer with, we write Wn as the kind of the set of words of length n with letters like alphabet 1, 2. So each of the element is W0 to Wn minus 1, and each letter is either 1 or 2. And we kind of want to use the dynamics, like this propagation thing here, to refine this partition. So we want to write for each word, I want to write the corresponding operator is for the last one we don't propagate. The previous one propagated by time 1, and then time 2, and so on. And then we multiply them together. And obviously, we'll have the following final partition, like this. Okay. And for each of AW is corresponding to a symbol, which is, not surprisingly, by the Egorov theorem, is propagation the AWJ by time j and multiply together. So, so you can think of each of these for n larger and larger, this will be kind of a more and more finer partition of the S star m. Okay, of course, eventually we want this n to be like a row of times log 1 over h. So this still works, but in this either this one or this one, depending on which side you are propagating. And how do we use FUP here? Actually, the claim is for each of them, this satisfies this FUP condition. If we choose the length n to be twice of rho log 1 over h, we propagate forwardly rho log 1 over h and backwardly rho log 1 over h. And that's the time we are choosing. So let's capital N to be rho log 1 over h, maybe I guess this one. Then we can split this into the one W plus and W minus. So each will be the word of length rho of length rho times log 1 over h. And actually here, it's a little tricky here. I want to also write this Okay, so maybe I shouldn't write this, sorry. Because there is another propagation here, so also want to propagate, conjugate this by u times minus n here. And so W is okay, and so this one will be in the class SL. Let me think which one is which one. Sorry, if I can. Stable. This one is stable. Let me see. Right, we always choose this stable, and this will be the unstable one. And now the final claim, of course, is we have to check the porosity thing. So if both of the support are porous in our condition here, then we can claim the FUP for word is that.
How did you split up? What are the definitions of W plus minus?
Oh, well, you just split this part. It's
Concatenate the
You just
first.
take it.
right. The first n letter, the last n letter, and then put them together, and we'll write it in this way. And this one will be in the unstable one. This will be the stable one. And so the
So here they will use a single sequence.
yes, W is a single sequence, right? So basically, we are saying that any single sequence, what you get is satisfied by porosity condition. Of course, I don't have time to really explain this porosity condition, I guess. So the point is, the porosity really coming from the hyperbolicity of the geodesic flow and the unique ergodicity of the cyclic flow, like the picture Semyon showed yesterday for the cat map. So, they are really porous. One in each in the correct direction, one in the stable direction, one in the unstable direction.
Basically, what I don't understand, I mean, so man has some decay. This was exactly sort of the key to her first paper, is to prove some kind of L2 decay of these AWs.
Right.
But here the difference is that the first, I mean the projector, if you want A2,
they're
is big,
different.
is very big.
Right.
It's not,
So here we are.
it's a big size, you know. So
It's not a fine
the paper,
partition.
Right.
Each element of the partition is relatively very small. No, small.
Right. So each element in
Here A2
right.
is big. Here A2 is big.
So it too includes a lot of, various ways you can be trapped.
Okay, so maybe now there are still more tricks in the proof, but let me maybe present a quick, pseudo proof with some laws here, with this simple idea here. Okay.
Wait, so I'm lost. So what are you going to know? So we have this main estimate and we have some
Right. So I'm going.
control over these norms of these AWs.
Right. So basically, we can't use them to sum directly because there are so many words of them. There are like h to the minus power of them. So what we are trying to do is we want to put the one which are actually passing through one together. This will be controlled part using our previous argument. And the red, there will be something rest, and those will be used FUP. Okay.
Now you're basically assuming this estimate on AW and you want
Uh,
to use the main estimate, is that what you're doing?
Yes, I'm going to do. And of course, to prove this, we have to prove that the support of both actually has to be porous. And unfortunately, I don't have much time on this. So
Can I ask you about that, what you just said? You
Yes.
can control the ones where you have, where the words.
Right.
There are enough ones in them. Or
yes, exactly.
So what words can't you control? I mean, if you just look at the W's, what words can't you control? They only stay in A2.
I think he's about to write out this.
Right, I'm going to write out how to get this from a slightly weaker version, and I'm going to say briefly what
Thing
happens.
is you only get like a very, like one or two words that don't go through A1.
Right.
Just one.
Okay, so right, so that's exactly I'm trying to do here. So let's basically separate this here with n equals 2n into two parts. So identity will be a sub x and sub a of y. So I use sets here to indicate the sum over all the words here. So x will be, I use x to be the trapped one. So there's only one word here, which everything is 2. And the y will be, of course, 2n sub x. Okay, see what happens. Okay, so this will be kind of the one which cannot control, and this will be kind of which we hope to control here. Okay, so we can write, basically we can write every u in terms of ax times u, ay times u. And ax times u obviously is 1. It's by the factor uncertainty principle. So ax fup. U. Okay. So what happens to ay here? So in ay, basically for each word in y, you have at least 1. One of the letter is 1. So okay, so 1 of 1. Okay. And we write y as kind of disjoint union of the following set. So YL is the word which letters the letters are 2 if k is bigger than L, and WL is 1. So basically the first one appears at L if you going from the order. Okay, then basically we do this simple triangle inequality saying AY can be controlled by all of them. So AY of U can be controlled by sum of AYL of U. But what is AYL? AYL basically this is 1 and everything after is 2. So we can basically sum them together. So we'll get AYL sum everything here is 1 until we hit A, if I get it correctly, so A2. Okay, because of actually the last one is A1L, and because I'm using backwardly, so all the others are 2 here. 1 minus 1, 2, L plus 1. Okay, and I can throw basically, I think now we can throw out everything here. So AYLU is less or equal to A1L of U. And by our propagation estimate, is A1 can be controlled by A, so AU, a constant, plus L, a constant, over H, and minus H squared minus 1 Laplacian U. Okay. Okay, so, and then we sum them up. Of course, we almost get this, except the problem is our n is log 1 over h. So we get extra log 1 over h here, and another extra log 1 over h here. So we are not yet done here. So I think to kind of correct this thing, we again borrow kind of one of Anna Thurman's argument here. We want to, let me just wave a hand about what I'm trying to do here. I'm putting more words in X and less words in Y. The more words in X basically are the ones which has a proportional, which means the one in Y will have a proportional of letters which is 1. And X is everything else. And if we choose that proportional very small, I guess, then we should proportional large enough here, then this set will be still controllable by h to some power which is depending on the proportional we have. And if we choose that small enough, we can large enough, we can actually control this part still using FUP. And what's left will be controlled by a kind of a finite step of this instead of log 1 over h step. And that will basically kill the log 1 over h factor here. Okay, sorry for going over, but that's all. Thank you.